Right, so now let's move on to the formal definitions of functions. When we work with a function, the basic thing that you have to remember is the Cartesian plane. That's the basic thing, right? So it's x and y. When we worked with trigonometry, I said the purpose of the Cartesian plane is to orientate something in space. We want to know precisely where does it lie in space, and the way we do that is with a coordinate, right? So we'll have an x and a y coordinate. Now, when we work with functions, we talk about domain and range. The domain of the function is the x values, right? And the range of the function is the y values. And so if I have to plot this function, let's say I plot this function here, right? The x values for which this function exists is here. Look at this. It's this x value all the way down to this x value here. And so for all of these x values, when you input it into the equation, this function exists, right? And if you have to look at the y values, then you'll draw a line to the y-axis here, and you'll draw a line to the y-axis here, and it's all these y values the function exists for. Now remember, it's all of the values that lie in between these extremes, right? And this is why inequalities will come into play now. Because inequalities, we're saying that there's a range of values that will satisfy the domain. It's not one value, there's a range of it. It's the range is from here all the way to here. Because if you input any value, let's say if I choose this value at random, if I input that value into this equation or into this function, the function does exist at that point. If I pinpoint another value like here, if I input this value into the equation or the function, it will output another y value. So this is why we say that the domain of the function is the set of x values that the function exists, and the range of the function is the y values that the function exists, right? Now, what's important, I brought these two terminologies before, set and set. So when we're talking about a function, there's two sets that make up a function. And one set makes up the x values, the independent variable, and the other set makes up the y values, the dependent variable, which is the same as the domain and the range. And so these two distinct sets make up the function. And again, when we work with sets, they do not say it's like a collection of things. In this case, it's a collection of numbers. So you're going to see how we're going to link everything from inequalities all the way down to linear equations, quadratic equations, and exponential equations. And it's all going to make sense. So let's do this again. When we work with this, the domain of a function is the x values for which the function exists, and the range of a function is the y values for which the function exists. Now, see these, because I got these 2 endpoints kept, that means a function will not go past that. I can do something like this. I can have the same function and I can put arrowheads. And what this arrowhead means is that it extends indefinitely to the right and indefinitely to the left. And so this function exists for all x values. And so that's why when we go back to what now? The number system. If it exists for all x values, means the x value could be an integer, it could be a whole number, it could be a natural number, it could be a fraction, it could be irrational, right? It could be any of those numbers. But we can collectively say that it could be what? Real. And remember the notation for real. This is this here, real, like this. And so we say x element of real. So this is the function. We have some function f of x is equal to 2x squared plus 2. The x values that I can input into this function can be any real value because it exists for any real value, right? And then we'll have a range is what y values do the function exist for. And so let's apply to this function here. Let's say that the equation of this function is y is equal to x minus 1. If I look at this function, there's no restrictions. It can go indefinitely that way and indefinitely this way. And so what we'll do is we can say that it's x element of real. What does this mean? Remember, this is the function, this is the input, that's the output. So exactly as I said, x, you apply a function to x, you get a y value. What x values can I input here? That's what the domain tells you. What y values did I get out from it? That's what the range tells you, right? So if I look at this function and if I analyze it, I can see that I can put any x values. It can be any real value. So that's what the domain will tell you. What outputs do I get? I get any, it can be any value. If I drop a line here to the y-axis to see, if I put a ruler and I mark these points on the y-axis, I can go infinitely upward and infinitely downward. And so therefore we can say y is an element of real. Remember, these arrowheads are very important because it's telling you it extends indefinitely. There is no restriction. There is no maximum or minimum. It can go indefinitely in either of these directions. And so for what y values does this function exist? It can be any real value, right? And so that's how we're defining it in terms of domain and range. So the domain and range is giving meaning to the function by telling you where it exists. That's all it does. It just tells you that it exists for all x value and all y values. So that's how we use the domain and range to understand the function, right? But the shape of the function comes from the function itself. So what's the function? Like, this is a quadratic function. Here, this is a linear function. So that's what you need to remember. Right, so now if you want to understand this idea from the perspective of domain and range, this is how we will do it. And this is the way it works. We have two sets. There's a set A, like a box or a container of things inside, and here's a set B, a box and container of things. What A represents is inputs, and what B represents is outputs. Then we have some function which is x squared. So what x is the independent variable. We have a function. What the function does is it transforms or translates x. So what is the function doing to x in this case? It is multiplying it by itself, or it's squaring x. That's what the function is doing, and we'll get some output y, right? Then we give this graph a name. We're calling the graph f. We're giving it a name, right? You may not understand this fully, but when we get to it, you'll understand precisely what I'm saying. F is the name of the graph. So f is the name of the graph, x is the input, and x squared is what the function is, right? The function is we're taking it and we're squaring the x values, and whatever we output should be your y value. And so what we do is, when I input 1 into this function, what do I get? 1. When I input 2 into this function here, what do I get? 4. Do the same with 3, you get 9, 4, 16, 5, 25, and 6 is 36. And so what we do is, for every input, there's a output like this. So we can do these arrowheads onto each of these outputs. So from x, it maps it there. For this x value, it maps it to 4. From this x value, it maps it to 9. And what's very important is for every element that you input, there's a unique element as the output. Remember when I brought up the definition, I said that for every input, there must be a single output. These two words will become very important at grade 12, a unique element. And so this is what we mean, right? 1 goes only to 1. It goes to only one value in the other set. It doesn't do this. Look here, this here. Go to 2 values. If only the function does this, then it's not a function. If it only does this here, then this is not a function. It could be a relationship, but it's not a function. Because a function can only exist when an input gives you a single output. This is why we say a unique element. Right? It can't be 2 elements giving from a single input. It can't be 2 outputs coming from a single input. Then that would not exist. The function would not exist. The relationship could exist, but the function won't. Right? And so you can see here, as I denoted here with this oval, it represents the values on the x-axis. So what are the inputs? What are the possible inputs that I can put into this function? Right? It's x element of A. This means that x is a part of this set of A. Right? And so in the same way, we could, when we're defining functions, we'll say x element of real. And so you can think of this oval as being a container that holds every possible number, rational, irrational, natural, whole number, and integers. And so this x is a part of the set. It comes from that set. It's an element of this set. Understood? And then we talk about the y values, we can do other things that we will learn later on in the videos. But this is what you need to understand. This is how functions are born. They come from an input and an output. And this is how it goes. And the most important part that you need to remember is that a function, for every input, you cannot have 2 outputs. Then you don't have a function. You have a relationship, but not a function. 2 distinct things that you need to understand. Right, so let's look at the other ways of representing a function. So this was understanding the function from the standpoint of a domain and range. The other ways that we can represent a function is using a table, the graphical standpoint, the very important one, or the algebraic standpoint, which is mapping notation and function notation. This is what you'll see all of the times. The algebraic way is what? Using numbers, variables, and operations. The graphical way is what? Obviously drawing the graph itself, and the table method will obviously be having a table, showing the x values, showing the y values, and what the inputs and outputs are. Right, so let's look at this function here, y is equal to x squared. All you got to remember, you don't even have to know this function. All you got to remember is that you have a y value and you have an x value. The function is x squared, but what are we inputting? We're inputting x and we will get some y value out. This is the function, this is the input, and this is the output. Okay? But all of the functions that we will work with, the linear function, the parabolic function, exponential function, and the hyperbolic function, all of them will have a input that will output a single unique element. So you don't have to worry about whether the function exists. It will exist. That's all I'm saying, right? But I just gave you that as an additional piece of information so that when you get to higher grades, you understand. So long as there's a single output, that function will exist. Relationships can be whatever, but functions, they have to be a single output for every input, right? So let's look at it from the algebraic standpoint, right? These are the algebraic standpoints. The first one is what we call mapping notation, exactly as I've explained here. This is what it means. F maps x to x squared. That's how we say it verbally. F maps x to x squared. So f is the name of the graph. So if I had to draw this graph here, this is the f graph. It's called the f graph. And why would that become significant? Because if I had many graphs on this, you need to name it. Call this the G graph. So it's about naming the graph and giving it, a specific name. And then we have x here, we have y here, and what the function is, right? How does the function basically transforms x, right? It transforms and translates it. That's what the function does. So that's what it does to x to get an output, right? And so what that function is x squared. And what the outputs are is y, right? In terms of functional notation, the one that we will use very often, if not more all of the time, it'll be f of x is equal to x squared. So f is the name of the function, x is obviously the input, and f of x is the y value, the output, right? So if you look at it from here, just to clarify this, see here, x is the input, look at this, f is the name of the function, and f of x is the output. So this is y, this is the function, right? And this is x, the input, right? So that's how we're going to remember it. So remember, this is notation. You cannot challenge notation. This has been universally accepted by mathematicians. So we're just using it, right? So that's what you need to remember. And I've talked about those two guiding principles at the beginning for the exact reason. Because you're probably looking at this and you're trying to question why is it that way. You can't question something that has already been universally accepted. Because it could have been some other way, but we've chosen this way to be the convention. Understood? We could have used other letters for the alphabet, but we chose the A, B's, and C's. And that's how we've used it our entire life, right? It's worth noting that the functional notation and the mapping notation can be used interchangeably. So these two ways can be used interchangeably. So let me just emphasize something. These three ways are just three different ways of representing a function. You can choose whatever you wish. You can use any of these ways to represent a function and you will have a function. Right, so do not confuse a function with a graph, because when you look at a graph, you'll think that's a function. No, it's a way of representing a function. Big difference. All right, from a graphical standpoint, if I had to sketch this function, it would look exactly like this here, exactly as I drew it here. Right, and obviously we have to label it. If I look at it from the standpoint of the table, if I put in 1 into x squared, what should I output? 1 squared is what? 1. If I put in 2, right, if I put in 2 into x squared, what should I output? 4. If I put in 3 into x squared, what should I output? 9. If I put in 4 into x squared, what should I output? 16. And so that's what we're doing, input, function, output, isn't it? And so that's how you will represent it using a table. Remember, these are just three different ways, three different categories of representing a function. Three different ways. And so when you're talking about a function, you need to know what representation you're required to use. And what's significant about this is what we will use a lot. The graphical representation is extremely important for the reasons that I've already mentioned at the beginning. Numbers and words can be very abstract, but when you apply a graph to it, you can deduce relationships and deduce patterns from it that you can't see. Can you see any pattern from this? I can't see any pattern, but when I put it in terms of a graph, I can see a pattern. Right, so it's all about pattern recognition. We're using pattern recognition the right way. Right? We're not learning it by just repeatedly doing questions. Okay? So now let's move on to some of the stuff that we're going to learn here. Before we proceed with our discussion on functions, I have to mention the fact that with all functions, we have what we call a parent function. I've talked about that when we learned standards under the guiding principles of standards, which is the primary function without translations and transformations. It is this function that gives the definition to the linear, parabolic, hyperbolic, and exponential function. To me, the combination of functions and algebra helps you understand all other topics in mathematics. When we view the solutions in the example problems for algebra and the solutions to the DBE questions, you will see that I make use of functions extensively, right? Again, after we do this course, I will go back to term 1 work and I will show you how everything fits, right? So the only thing that you need to remember here is the parent function, right? Because what is the basic definition of a linear function? We need a basic definition for it in order for us to make use of it, right? And then we can start modifying it and doing whatever we want. That's what's significant. What's the basic definition of a parabolic function? We need to know that definition so that we can start making modifications and work with much more complicated questions. The fact that this exists means there have to be a definition for it. Extremely important stuff. The fact that words exist means that there has to be a basic definition for it. People may use it differently in different contexts, but there's a basic definition, there's a standard that you can go into the dictionary and follow strictly so that we understand the definition of that word that we universally have to accept. Right, even here too, the hyperbolic function. What's the basic definition of a hyperbolic function that everyone has to abide by and everyone has to accept as the basic definition? And so should you, listen to this is why definitions are so important. Because should you deviate from the definition, then you are not talking about a linear function, you're talking about something else. And this is why you get questions wrong, because you're not abiding by the definition, right? When we talk about the exponential function, there's certain definitions that we have to know. Again, why are definitions so important? When I spoke about the guiding principle, because it talks about the constraints under which that topic applies. And so exactly as I said, if you deviate from that, then you are talking about something entirely new that's not pertinent to the topic at hand. Right? So this is why you need to understand this. Right? Exactly as I said here, before we discuss the practical use of functions, we will first view each function from a mathematical point of view, like sketching, interpretation, and reading the graph. Then we'll come back to the practical nature. Why is this important? Like I said, there's certain things of the graph, there's certain components of the graph that's extremely important that we must know. And why those components are important? Because it will enable us, because remember, if I gave you a blank piece of paper, the fact that we choose to put certain things on it means it's significant. And so when you're given a graph, it could be very abstract. Itself could be very abstract. But this is why we pinpoint certain things so you know where to direct your eye to. And you know what you're reading. You're not just mindlessly looking at a graph and trying to deduce information from it. You can't if you don't understand the components of it. So let's finally move over to the linear, the parabolic function, the hyperbolic function, exponential function, and understand the different components of it.